Welcome to Ready to Derive. I'm rather proud of the title of this video because of the play on words. So while it is the case that we will actually learn the ground rules for working with derivative, it's also the case that differentiation actually rules. It's the means by which we are able to solve many real-world problems, as we will discover later in the course. The rules presented in this video may seem obvious and perhaps even a bit trivial to state, but it's important to be comfortable and confident in the application before moving on to more advanced differentiation techniques. So, without further ado, let's get started.
So before getting into the derivative rules, I'd like to introduce new derivative notation. So when we use function notations like f of x equals x to the 10, if we'd like to indicate the derivative, we use the notation f prime of x. And this is just the power rule being used, which was just introduced in the previous video. If we are using y equals x to the 10th, then the notation that the derivative notation now is dy by dx. Remember, dy by dx is a Leibniz notation. It kind of gets at the idea of rise over run, akin to delta y over delta x. So now what we're going to do is we introduce a new notation that kind of condenses what's going on. So in both of these cases, notice that you start with identifying the function. That's one statement, and then the second statement identifies the derivative. So what if it could just be one-stop shopping? So why not? What about this? Instead of saying, well, y equals x to the 10th, and then what's dy by dx, notice that instead of having y here, we just replace y with what it is. So we replace y with x to the 10th, and we have this instruction. So it looks incomplete. What does that d over dx mean? It reads d by dx. So you say, to read this statement, you say d by dx of x to the 10th is 10x to the 9th. And what it means is the derivative of x to the 10th is 10x to the 9th. So think of this d by dx as instructions to take the derivative of whatever function is in the parentheses here. So it's instructions. Another way to think of it is like an operator, in the same way that cosine and log are operators. They don't just exist independently of anything. You can't just have cosine by itself. It has to be the cosine of something, like pi, the log of something, like 10 to the 3rd. Similarly for d by dx, it has to be the derivative of a function. So the first derivative rule is one we've already seen before. It's such an important one that we devoted a whole video to it, and that's the power rule. So just to recap, that's d by dx, or the derivative of x to the n, is just given by n x to the n minus 1. So let's do a couple of examples just to refresh our memory. So d by dx, again, the derivative of x to the 10, we drop the exponent down, 10x, and then we subtract 1 from the exponent, so we get 10x to the 9. And just one more, we can also do it with negative exponents. Remember, n is any real number, so this would be negative 1x, and subtracting 1 from negative 1 will give us negative 2. The next derivative rule is the derivative of a constant function. So as we know, the derivative of a function is just the slope of that function at any point. So let's look at a constant function. And this one here that I have graphed, let's see, it looks like it's passing through 2. So the equation of this would just be y equals 2. That's what a constant function looks like. And what is the slope at any point on this function? Well, because it's a horizontal line, the slope is always 0. So the slope, wherever you are, is always equal to 0. So therefore, we might say f of x. So if f of x equals 2 or y equals 2, whichever notation you would like to use, if f of x equals 2, then f prime x is equal to 0. Summing that up in our new notation means the derivative d by dx of a constant function, so c is a constant, is always 0. So as an example, I don't really need too many examples of this because it's pretty straightforward. The derivative d by dx of pi would just be 0. So now let's look at the constant multiplier rule. So this says the derivative of a constant, c stands for a constant, times a function is just the constant times the derivative of that function. it's like you're just extracting out the c, because the c does not depend on x, so you're allowed to do that. This should look familiar because there was the same similar law for limits, as since derivatives are just limits, it's not surprising the same rule applies. So if we think of, let's make an example, let's pretend c is a half. So what this is saying is that the derivative of half of f of x would just be half the derivative of f of x. This doesn't seem that profound, but let's look at a sketch of this. It might help to visualize it. So in this, I've made the green function is f of x, and the orange function is half f of x. So I just applied a vertical shrink of a half to that function. And so the derivative, if we would like, for example, the derivative here, it looks like about a half. I'm going to approximate it. Well, it looks like it's a half, and it turns out, well, the derivative here looks like it's 1. I guess you have to just take my word for it, but the derivative of the orange function at 0.1, i.e. the slope of the tangent line, is half, and the derivative on f of x is 1. So wherever you go along here, so whatever slope you consider on f of x, the corresponding slope on half f of x will be just half of that. And one way to think of that is if you think about it, when you're thinking about slope delta x and delta y, rise up or run, we're taking kind of a sort of crude example here because this isn't the instantaneous slope, but if you think about it, you're keeping the delta x the same, but because of your vertical shrink, you are shrinking the rise to half delta y. So it's not surprising that this relationship is true. So let's look at an example. So prior to this, we've only taken the derivatives of power functions with no coefficient in front of them. So just x to the 10th, for example. So now we have this coefficient of 1/10. So this is our c. So, and notice I'm changing the notation. I keep going back and forth with notation just to so you feel comfortable with it. If I'm using y, then I have to use dy by dx for the derivative. So what is the derivative? Well, according to this rule, we get to take out the 1/10, and then we can just focus in on the power function. So that 1/10 is still hanging out there, and the derivative of x to the 10th by the power rule is this. We notice that the 10s cancel out, and so the final answer is just x to the 9th. So now we have two rules folded into one, the sum and difference rules. So this is sort of common sense that the derivative of the sum or difference, notice that plus minus refers to the sum of the two functions, or the difference is just the sum or difference of the derivatives of the individual functions. This should seem familiar again to one of the limit laws. And because derivatives are in fact limits, it's not surprising that there's this parallel. So let's look at an example. So we have a quadratic function, and we need to find the derivative of this. And I'm kind of going to mix and match notation. So notice I've got f prime x as the designation for the derivative. But in employing the sum and difference rule, I'm going to kind of get into the weeds here and say, okay, so first of all, this is my first function. And first of all, I have a difference because of this minus here. So I'm going to use the rule above and say, well, that should be the difference of the individual derivatives. And then I have a sum here. So I'm going to just say, okay, I'll take the derivative of 2. And then if I'm going to be very particular, so as I look at this first derivative, I would use the constant multiplier rule to kind of extract the coefficient of 3, and I would get this. Similarly, I'd extract the 5, and I would have d by dx of x. And now, since I'm here, this last one here, the derivative of a constant function, I know is 0, so I'm just going to put that in right now. And then I would do 3, so the derivative of x squared is 2x by the power rule. The derivative of x is just 1, and we get 6x minus 5 as the answer. Now, this is, I've gone through all the detailed steps, but as you start to get familiar with the rules, you can take shortcuts. So for example, if I wanted to get directly to f prime x, I could realize that, well, the 2 drops down, multiplies by the 3, so I get 6x, drop the exponent down by 1, and then if I look at minus 5x, the derivative of minus 5x is just minus 5. You can see that's sort of much more efficient. So you don't need to show all the steps that I just demonstrated. As long as you understand them, you can take the shortcut, and that's much more efficient. Now we arrive at the product and quotient rules question mark. Right. So if we were sort of going along with the sum and difference rule, you might be tempted to think that the derivative of the product of two functions would just be the product of the derivatives. I'm going to change notation again because there's less writing. So you might be tempted to just take the individual derivatives and multiply them. And you wouldn't be faulted for doing that because that's what we did for the sum and difference of two functions. And in fact, there is the limit law, the corresponding limit law says you can take the product of the individual limits if you want the limit of a product. But this is not the case here. So I'm going to erase that here, pretend you never saw that. I don't want that committed to your memory. And I'm going to say that this is to be determined. So the product and quotient rules are not going to be revealed in this video. They merit their own video in the future. And so we have to kind of be prepared to deal with what looks like it might be a product situation. So here we have, say that's f, and this function here is g. You actually cannot take the derivative of it in that form. You have to actually put it in what I like to call power rule ready form. And that means you have to, in this case, just distribute. So x squared times x cubed is x to the 5th minus x squared. And then if you do that, then you can apply the power rule because we basically have it kind of in polynomial form, no products or quotients, and that would be the answer there. Similarly, if it's written as a quotient, so we have like a function f over g or g over f, whichever way you want to look at it. Notice that until I get it into power rule ready form, I have to keep that d by dx, so because I haven't yet taken the derivative. So I first distribute the x squared into both terms in the numerator, and I'm still not ready, so I'm going to keep that d by dx, and that's x cubed, x cubed over x squared is just going to simplify to x, minus x to the minus 2. And now I can take the derivative, so that would be 1 by the power rule plus 2x to the minus 3. So those I can manage. What I can't do just yet, until we have the product and quotient rules, is what I just introduced up here, what I just showed up here. So this is problematic because I cannot distribute, I have a binomial in the denominator, and there's no way I can kind of distribute that and get that into power rule ready form. So until the video on the product and quotient rules, this we cannot do. So we'll end with one practice problem. So I would like to find the derivative of this function, but I've left a gap here for a reason. The reason is I've got to first of all make sure that it's in power rule ready form. So these terms look fine. So I'm just going to bring them down, even plus root 10. But I have to convert that 3 over x squared into, make it into a power function. And also I need to rewrite the radical as x to the half. At this point, I'm ready to derive. Oh, pardon the pun. Okay, so I can now apply the power rule to each term. So the derivative of this, again, I'm not going to get into all the separate rules. I'm employing them all now. The sum and difference rule, the constant multiplier, the constant, it's all coming together. So in this one, I would pop down the 3 in front. So I would get 3, and that just multiplies by the a. It just sits like that, x squared. Here, I get to multiply the 2, and that will cancel with the denominator of 2, and I'll get pi x. Here I have a constant term, so I'll get 0. Here I will have the negative 2 will pop down and multiply by negative 3 to make plus 6x to the minus 3. And then the half will pop down here cancel with the 4 to make 2x to the minus half. Now, it's important sometimes to make sure you rewrite the derivative in the same form that the function appeared. So in other words, I have 6x to the minus 3 here, but if I convert that, if I get rid of the negative exponents, I would have to rewrite that 6 over x cubed because I started by giving you negative 3 over x squared. And similarly for the radical, I have that 2, x to the minus half, right? That's 1 over x to the half, just in itself. And that is a radical, x to the half is a radical, so I end up with 2 over radical x.